rectangles. And integrals just doing that with tiny rectangles. Infinite.
My mom was like,
What's the whole Riemann sum thing for his prime numbers that he has that?
Oh, the
Equate,
Riemann zeta
like-
function?
Yes.
That thing is insane.
Yeah, it's like a.
He's looking for the zeros of a specific function, and we think it's still an open question. It might be open till the day we die. We're not sure if it's even resolvable, but
Yeah,
he thinks he's got a function that the zeros of it are exactly the prime numbers. It's
Yeah.
strange that is.
that's what it is. Yeah, if you look on the graph, it looks crazy.
But that would mean that he found a function that generates primes that's never been done. So it's a humongous claim. And there's like branches of mathematics where they assume it's true and see what they can deduce if it's true. Other branches of mathematics where they assume it's false and see what they can deduce if it is false. So it's a crazy, not quite a theorem, but postulate that he put out.
I heard a mathematician once say that mathematics is not at a mature enough point that we can resolve that hypothesis.
Yeah, there's a lot of even simpler stuff that math can't even get on, like just strange little number games. And someone asks you, will this game end? People put in tons and tons of work, mathematics, analysis, all sorts of things, and it's still open. They can't figure out.
Like that 3x plus 1.
Yeah, there's a lot of weird little games like
Yeah,
that
was
where
crazy.
mathematics can't resolve that either, at least not yet. Well, math is weird. Welcome back, everyone. We're week 15. We meet 3 days a week. So this is like class number 45, if we assume we never canceled any of them. So welcome back, everyone. Our goal now is just to review more problems. And my thought was we kind of skip around and do problems that look like they'd be better candidates for a real final exam question. But before we do any of that, let's open up to the class. Any questions folks would like to start out with today? Yeah, go ahead. It will not, no. I felt like Newton's method, we had fun with it, but it was mainly mostly kind of a fluff topic. It was something we solved, but won't be on exam. Yeah, that's a good point as well. There's a couple exams down here. I did say they excluded questions, but I didn't look for the Newton's method and excluded it.
it's also an other one.
Mhm.
Yeah.
Yeah, our exam won't include that Newton's method. That was one where you're trying to solve some kind of nonlinear equation. Say, for example, let's go to 4.8 here. And imagine that you want to solve that equation.
Oh, talking about.
That's a hard equation to solve, but sometimes you just need a decimal approximation. If you grab a computer algebra system, even say Desmos, it can do this, maybe not Desmos. Desmos is just graphing, but a lot of computer algebra systems have a solve feature. And this is literally the kind of stuff it's doing, Newton's method. It's an iterative method using tangent lines and linearizations to give you successive approximations that get better and better, finding the actual zeros of whichever crazy function you come up with. It's a cool method, but for us, it was mostly probably one of the more interesting applications to calculus, but not a great candidate for a final exam question. Other questions so far? Okay, well, should we go and start cherry picking problems from here?
Yes.
All right, let's go for it. I feel like example 2, it's pretty interesting. It's actually important. But I don't think I'm going to give these kind of questions on a real final exam where we have to graph a derivative. That requires a cool head, a steady hand, probably not best in a slightly stressful environment for a final. Let's see, we ran through example 3.
Can I have a proposed one?
Yeah, absolutely.
Wanna look at concavities again?
Yeah, let's see if we have one down here. Let's find our concavity. This will be in chapter 4 somewhere. So minimums, mean value theorem, local min and local max. And here's concavity.
Yeah, this topic.
It is a pretty tricky topic. How about we go through the whole set? Local mins, local maxes, concavity, and inflection. That sound all right? Yeah, absolutely. And you're thinking for optimization, right? Okay, so after this one, we'll do an optimization.
Another one that we had like a question that one in the last exam we did at the very end, the pure variables.
Yeah, that was an optimization one.
Definitely, we should definitely go by that one.
Sounds great. Let's take a look. You know, we mentioned though, as a deal after exam 3, that there would be an optimization, but it's gonna be more filled out, less constants like A, B, C, K. Definitely do that. Awesome. All right, so let's start off with this here. We want to find local maximum minimum values. First step is just to differentiate that thing. So f prime of x. It's a logarithm, so it's going to drop x power 4 plus 27 down into a denominator. But really, for chain rule considerations, it's also going to look like this. The inner function x power 4 plus 27 goes here and here. So next step on the derivative, we'll have x power 4 plus 27 down below. Derivative of this one is just going to turn into 4x cubed. And that's our first derivative. No great simplification on it. That look right so far? Okay, if we're trying to find local mins and maxes, next thing we really want is a critical number. So we'll set that thing to 0 and solve it. We're multiplying both sides by x power 4 plus 27, but visually you're just feeding it to 0, so it's gone. The only way this equation is true is if the numerator is 0. The only way that's true is if x is 0. There's truly 3 solutions here, but we're only going for the real valued one. So we get the unique solution. X is 0, and this is the critical number.
So when you likely drop what's the denominator not matter in this?
Well, if we went for like a more complete solution on this one, the very first step we would take is to clear out that denominator. And it would look like this is a step. X power 4 plus 27. And then this is the step where we're pretty much just feeding it to the 0 and then wiping it out altogether.
So it can't.
Exactly. So really just your numerator that matters for a fraction set equal to 0. Other questions so far? Okay. Well, once we have a critical number, next thing we do is we take the entire real number line. This function is special. X power 4 plus 27 is always positive. Its minimum value is 27. So the domain this time is all real numbers, even though there's a logarithm. So we'll go here, give the full real number line. If there's multiple critical numbers, we have to make multiple cuts. But in this particular problem, there's just one. So here's our first cut point right at 0. And what we're doing with all this information is we need to know the sign of the first derivative. We need to know whether it's positive here or negative here. And that will tell us if the function is increasing or decreasing. So we're converting to essentially what's scratch work. Easiest number is -1. But notice that that's x power, or excuse me, that would have been a mistake. We're putting this inside f prime. Probably a good idea to put it up here just to start out as a reminder. F prime is this function, the -1 right here. All I want to do is pick any test value to the left of 0. -1 just happened to be the most convenient one, but any number would work for this thing. And likewise, to the right of 0, probably the easiest number to test would be a +1. Other questions so far? Okay, we're plugging all that into f prime. Let me just clear all those. So it's going right inside there. That's our first derivative. So let's write that out. F prime at -1. Up here, that's going to turn into a -4. And the denominator is positive no matter what. This would turn into a 28 after working it out. But like we mentioned before, it's not as important to the numerical value. What is important is that's negative. So we have less than 0 here, and it means we are decreasing on that entire range from -0 all the way to, or excuse me, from -infinity all the way to 0. Next, we just redo it, take the 1, plug it inside here. F prime at 1 now is 4 in the numerator, still 28 in the denominator, thanks to that power 4. It's just going to always be positive. So we have greater than 0 here, less than 0. And that means on this range, the first derivative is positive, which implies the function is increasing. So if we were to do a plot of the function right around 0, it went decreasing and then increasing And we are looking at a local minimum. So for the local maximum, we'll say none. F has no local max. It does have a local minimum, and in fact, that one would be an absolute minimum because it's always increasing to the right. Oh, hang on. Decreasing to increasing. Yes. Oh, it's decreasing and then increasing in that kind of way. I just confused myself in a weird way. This one's not just a local minimum, it's an absolute minimum. If you write your answer in as local minimum, that's completely fine. But I think the cooler answer on this one is the local minimum is an absolute minimum, which is going to be equal to, now we go to this step. We want the actual function value, so we have to return to the original function and write f of 0, the critical number. F of 0 is just going to be 0 right here. It'll turn into the natural logarithm of 27. So we did it, folks. That's the end answer on this one. And there's often a really good question about this. Why didn't we, just the moment we found a critical number, plug it into the function? One reason is we need to know if it was a minimum or a max by looking at this graph, but probably even more importantly, there's nothing stopping your function from doing this. That has neither a minimum nor a maximum anywhere on this domain for our function, but because we detected it was increasing, we excluded this, and we knew we really did have a local minimum. That happened to be an absolute minimum in this problem. So it goes like this, right around that location for that value. Yeah.
So we would have had an increasing on the left side and decreasing on the right. We assume it'd be the opposite rather than it'd even have an absolute maximum.
Yeah, exactly. Yeah. So it's always good to kind of visualize it as you're building it together, just to give our brain a little bit more traction on getting through the problem. Now we go to your question. We're looking at concavity. And we'll recall what the next method should be if we're going to find concavity of this function. Exactly. This is now the second derivative test for concavity. So we already have f prime right here. Think of this as also a review in the quotient rule. Now we'll do f double prime. So f double prime at x. First thing we do is take the derivative of the top. You could write in the bottom function first and then the derivative. But either way we write it, this has to be differentiated first, or else we made a small sign error. So this one will turn into 12x squared to start. It's multiplied by x power 4 plus 27. And then go minus. Next, copy in 4x cubed. And it gets multiplied by the derivative of the bottom, which we've done before. That turns into 4x cubed. That's kind of curious. Looks like interesting symmetry right there. Whole thing is now divided by x power 4 plus 27 squared. So there's our second derivative. And we definitely want to painstakingly simplify this as much as it's feasibly algebraically possible, because just like before, we have to work with it in equation solving and also evaluations. So more time we spend here, the better. Let's work this out as first distribute 12x squared inside. We'll get 12x power 6 plus large number. Let's get a calculator going. So I need 12 by 27. Good news is calculators are allowed on exams. Don't forget yours. I'll definitely have spares, but I don't have a ton of spares. So 324 x squared after the next distribution. Now this one's going to turn into negative 16 x power 6. And down below, no change. Last thing to do is combine our like terms on this. We have 12x squared minus 16 of them. So altogether, we're looking at negative 4x power 6 plus 324x squared, all divided by x power 4 plus 27 squared. This is turning into a longer problem than I anticipated. It still simplifies, but this time, this kind of simplification we want is by factoring. So let's factor out let's say -4x squared. Let's double check, that should divide 324. Oh, geez, not that though. I think I hit F11. There we go. So we're going to take 324, divide by 4, leaves it 81. That's a perfect square, so this problem is definitely looking kind of rigged. The numbers are nice here. So next, take out a -4x squared. From here, that's going to leave behind x to the power 4. And here, because we're factoring out a negative, this will leave -81. Just 81. Forgot we're factoring out x squared as well. So that's the factoring portion. Still divided by x power 4 plus 27. And there's a couple more steps here, but just to help our writing, let's do a little bit of this work in the margin. X power 4 minus 81 also factors. So x power 4 minus 81. We can do a difference of squares as x squared plus 9, x squared minus 9 to start. This one does not factor. You need complex numbers to make that happen. But a difference of squares, again, continues to factor nicely. Next line is x power 2 plus 9. X squared minus 9 becomes x plus 3 times x minus 3. So that's the factorization of this term right here. And I think this will be our last line for simplifying the second derivative. -4x squared times x squared plus 9, x plus 3, x minus 3, all over, oh, and I forgot a power 2 there, x power 4 plus 27, and here's that power 2 again. So we've got it, folks. That's, for our purposes, it's most simplified form that we can get to. Next thing we're going to do is set it to 0 and solve that equation. The only possible way that this is true is if the numerator is 0, but the only way your numerator can go to 0 is if you place a 0 there. So our solutions look like this. X equals 0. No values come from this one because you need complex numbers. You would need a 3i or a -3i. But we do get one from here, that's -3. And one from here, which is +3. So those are the zeros of the second derivative, and that means these are the critical numbers. Any questions at all, folks, on getting those values so far? Okay, what's kind of weird about this is not all of our critical numbers are equal. For example, this 0 is special. It came from x, which was to a power 2, so that one has multiplicity 2. And knowing you have an even multiplicity is sometimes kind of interesting on these kinds of problems. Now the -3 came from here, +3 came from here, and the powers are all 1. So these came from multiplicity, or excuse me, our multiplicity 1. That's right, multiplicity equals 1. And an even multiplicity is kind of weird on your diagram. Let's make a mention of it as we go through this next portion. Now again, the denominator is nice. We're not picking up any special critical numbers where the second derivative is undefined because there's no way to make that 0 with real numbers. So our range for concavity goes from -infinity to +infinity on this thing. And let's place our critical numbers. -3, 0, +3. This is the one with multiplicity 2. Deserves a special mention. And now we need to find the sign of the second derivative in 1, 2, 3, 4 different locations. That's a lot of work, but that's why sometimes it's a good to think in terms of multiplicities. If you do this just right, you really only have to test one interval. However, on a final exam, it's not a bad idea to test all of them just as an extra check. Things are working the way we intend. So first thing we'll do is go to this infinitely long range, pick a convenient value, -4 will do the job. Then we take -4 and we're plugging it into the second derivative. It's right here, but you wouldn't want to use this format. You'd want to put it in this format. Let's write that out. F double prime at -4. Well, it's going to start as -4, then -4 squared, and then here it's -4 squared plus 9. Over here it gets pretty interesting. This will turn into a -1. And here, this will be a -7. Down below, -4 to power 4. Well, nothing really matters down here because the outer power is 2, and also the function at the bottom is always positive. Well, let's write it out anyways. -4 power 4 plus 27 squared. So that's the whole expression, but the only negative signs that actually matter are this one, and this one. The rest are completely irrelevant in this problem, and that's because this is always positive because of the power 2. This quantity is always positive because of the power 2, and same from this and the power 4. So we have an answer that's negative, 3 negative signs altogether. Let's put less than 0. Does that make sense to folks on analyzing this crazy mess here? Okay, the value of just looking at your negative signs is you really don't want to put all of that in your calculator. It's way too many steps. And honestly, if I was putting that in a calculator on a timed exam, I have a high chance of just messing it up, miskeying something, and getting the wrong sign anyways. Just visualize what happens when you put in the number and where all of your negative signs are that come out negative, the ones that matter. So here, F double prime is negative in this region. Here's where the shortcut comes into play. This is a come point of -3 with multiplicity 1, and at odd multiplicity, the sign must flip. F double prime is less than 0 right here. Then we go to this 0. Multiplicity is 2, which is even, and at an even multiplicity, there is a repeated sign. So if it's negative here, it's negative over here as well. Next, this one has odd, so it should flip again. Yes, question first? Oh, shoot, it did not. Thanks for spotting that. So from here to here, I forgot to actually flip the sign. Saying it doesn't really do enough. You have to actually write it in. Thanks for spotting that. So at -3, it flips because of the odd multiplicity, stays the same direction there, so greater than, and then flips one more time, F double prime less than 0 in that range. Thanks for spotting that mistake there. Other questions so far, folks? Yeah, in the middle, it's positive. Then right at 0, we have no concavity, but then positive again right here. Yes. Other questions so far? Okay, like I mentioned, this strategy is great. Let's add just a little bit more detail if you decide to use it. It's a big time saver. That's where it shines. At multiplicity 2, sign flips. Or sorry, I am not writing down the right thing there. Let me try again. At a multiplicity 2, it's even. So the sign stays the same. Now on this one wasn't the major thing. The major thing was that multiplicity is odd. And so the sign flips. Sorry for this false start on that thing there. Again, it's a huge time saver. If you had extra time on an exam, it's not a bad idea to test some more regions and be suspicious just to make sure things are going right. I mean, for example, I put in less than here. That one wasn't right. I'll leave it to the class though. Should we test out a couple more regions? Okay, about this, let's go to the punchline. We'll now say for this one where it's negative and this one where it's negative, that's concave down. These are concave up. And so the overall conclusion is that F is concave down. Oh, that one. Yeah, that one is a second derivative test for local maximums, local minimums, or it can be adapted for absolute maxes, absolute minimums. Yes, so that one is with optimization. And that's what makes optimization tricky. Sometimes you want that second derivative test, Other times you need to avoid it like the plague, because it could be very involved. So yeah, we did one for just concavity here.
I was getting that one. I'm having that. I think it's just the whole second.
Yeah, I see what you mean. So F is concave down on, sorry, go ahead.
Yeah, so it was like, so like if I said here, if it's a constant, like a positive, then that is an absolute. That was, is that what you're saying, absolute? Or are there other ways?
Sorry, so what was the first part you said there?
Maybe later, can you just problem that like uses the second derivative test to the absolute?
Oh yeah, absolutely. Let's make sure we go for that one as well. So we'll do after this one, optimization, then right after that, we'll do second derivative test for optimization. Okay, so let's finish off this one here. F is concave down on this range. Negative infinity up to -3. Parenthesis around 3 because right here, there is no concavity. -3, F at -3 is the inflection point where concavity changes. So we'll go, say union, go way over here, and 3 to infinity. Next, to finish this off, we'll say, and is concave up. On this one's tricky. I would give a full credit to an answer -3 to 3. I probably would just put a small comment on the paper, but the most correct answer would look like this. Concave up on -3. Exactly. That's where the derivative is 0 specifically. It has no concavity there, neither up nor down. So -3 to 0, union 0 to 3. That's really kind of just a technical issue. I try not to nickel and dime people on points over smaller stuff like that, but it is good to be aware of. Just like with, say, increasing and decreasing here, right at 0, it's neither increasing nor decreasing. That's where it's constant for just a moment, or at rest if you're thinking something moving around. Well, any questions, folks, about this concavity test here? Okay, and just to tie together the notes, we did concave down on those regions and concave up on those regions. It just depended on the sign of the second derivative. Let's go next to some kind of optimization. Let's see what is on these notes, and let me know if you want a different kind of problem based off what we see here. Then after that, we'll go to the second derivative for maximizing.
How crazy is the chain rule gonna get in the final?
I would say not too bad.
Is it gonna be similar to the chain rule, like the example we did that one with chain rule? Probably similar to that.
Probably, yeah. I think if you go through, say, some of these problems here on the derivatives, or these are integrals, that's going the wrong way. Let's see, what's the worst one on here? Or they're honestly not too bad. And that's about how the final exam is going to be. I'd say what you did in homework for chapter 3 is probably the hardest derivatives you see in the class. Then the exam, had ones that weren't so bad. The final exam is going to be the same kind of thing. It'll be some of the more routine problems that you've seen.
In the exam, there was some crazy chain rule.
There was for sure. Which one? There is, yes. This function we could differentiate, as oddly as it seems. We'd use the fundamental theorem of calculus part 1 to differentiate that function. Should we differentiate it now that we're looking at it? Okay. So let's take a look at that optimization one. Let's see here. Now that would be half-life. So let's go down to chapter 4 is where we should be looking. This one is optimization, but there's no context here. So we need one that's a little bit more in the spirit of what we're looking for. Maybe number 16. The range of an artillery shell fired at an angle theta measured in degrees. The US Army is very familiar with this optimization. With horizontal, or let me read this again. Range of an artillery shell fired at an angle theta measured with the horizontal. Oh, so I think they're saying your gun is right here, and that's theta. So we're firing an artillery shell in that kind of way. Okay, so it's the range is given by this function. V naught squared looks like it's the muzzle velocity of the shell in feet per second. G is going to be the acceleration, constant acceleration due to gravity. And Sine 2 theta, well, that's somehow involved in this problem. We want to find the angle of the gun that will give it the maximum range. And that's how you'd be able to tell with whatever this is. Maybe it's on a warship, maybe it's a howitzer. You would know the effective range of that weapon. So that's a problem on this one. How do folks feel about it? Should we go for this or something else?
Oh, yeah.
Okay, let's give this a try. First thing we need to do is we want to analyze, and we're trying to maximize this. First thing to take a look at is what are the constants? V naught is the muzzle velocity of the shell in feet per second. That ought to be constant. They didn't say it specifically, but how do you folks feel about that? Does that feel constant?
For sure.
Awesome. That will make our problem definitely a lot easier. So we have a constant here. G is, now they helped us here. They told us it's constant, so that's helpful. Now let's say V naught squared and G are constants. This helps us a lot because now when we go to differentiate, think of all that stuff like number 5, something like that. You'll take the derivative and focus on sine 2 theta as you differentiate. Okay, so now we know what's going on in the problem. Whichever procedure we decide to use, we're going to have to differentiate that, so we might as well do it immediately. You could call R prime or dr d theta. Theta is not a bad choice here, or excuse me, Leibniz is not a bad choice because the variable is non-standard. The dependent variable R, independent variable being theta. So the thing that we're manipulating is the angle of that gun, theta itself. That's our independent variable. When we go to differentiate, the constant here is unaffected by the constant multiple rule. We just write in V naught squared over G. Next, we're differentiating sine 2 theta. Derivative of sine turns into a cosine. We have to multiply by the derivative of the inner function through the chain rule. I forgot to do this earlier. Just for the sake of maintaining our pattern from before, sine is the outer function. We differentiate it first, and there it is as a cosine. 2 theta is the inner function. And what the inner function always does is goes inside cosine, the outer function, completely unadulterated, just the way it is. Then it comes over here where we will differentiate it. But derivative of 2 theta is just a 2. So this is turning into 2 V naught squared over G times cosine 2 theta. Kind of nervous having a trig function there. That means we might have to solve a trigonometric equation, but that's okay. Now, we have to make a judgment call next. We have to decide, should we use the first derivative test or should we use the second derivative test? And usually the advice goes, if you think the second derivative is going to be easy, that might be the better test. And if the second derivative just looks like it's going to be a bunch of mess to get through, probably stick with the first derivative test. I'll leave it up to the class. We should be able to resolve it either way. Awesome. That kind of resolves your question as well about working the second derivative test. So let's stick with that one. Let's use second derivative test. Yeah, absolutely. Let's keep on running through. In Leibniz, the second derivative, I'm glad you mentioned that, is d2r. This is saying we're differentiating the r function twice. Down below, we say theta to say both times we differentiate, it's now with respect to theta. Now, in calculus 3, if there's multiple variables here, sometimes we might say d theta, then maybe d phi next, to say first differentiate with respect to theta, then differentiate for your second derivative, the other variable, something along those lines. That's why this Leibniz notation looks kind of funky in a certain sense. But it's the same sort of derivative. That's still constant, so we copy it in. 2 V naught squared divided by G. Differentiating cosine, same exact process as here. Cosine is differentiated first, which will give us a negative sign. 2 theta is the inner function, so it goes in both of these locations. And so now this is still a 2. We're going to multiply it by this 2 and the negative sign. So we'll have negative 4 V naught squared divided by G, and this is multiplied by sine 2 theta. So we now have a second derivative. Let me just double check this for correctness. Does that look right to folks so far? Okay, so with that second derivative in play, I did do one step kind of out of order here. Once you get the first derivative down, even if you're going for the second derivative test, exactly, we should have done that right away, right after. It doesn't matter the order you do this stuff, but it sometimes flows a little bit better as a process.
You're lost in the sauce.
What's that?
You're lost in the sauce.
Yeah. So we've got through the derivatives. Now let's go back to the first derivative right here. We're going to set that to 0 and get our critical number. Again, that's a little bit nerve-wracking. We're solving now a trigonometric function. That always requires a little bit of extra care. So 2v naught g times cosine 2 theta is 0. The only way that's true is if the constant is 0. That's impossible. They're all positive quantities. Or here is the possible offender. Cosine 2 theta might be 0. So let's write our next step. Cosine 2 theta equals 0. And now our goal is to solve that equation. No, the real final exam is going to have an easier question, or easier equation on this phase. So let me just say that right now. When I write the final exam, I also solve it. And it feels like we see stuff like this, which we didn't do a lot in class, it would probably change the question. But let's keep on going through it. To solve cosine 2 theta equals 0, first thing we ought to take a look at is the unit circle diagram. But also, let's look at the problem itself. Recall, we're aiming a gun, and we're never going to aim it vertically upwards, right? That seems kind of suicidal in a sense. Probably the only valid range here is going to be from 0 all the way up to pi over 2. Probably exclusive. We probably wouldn't set it to pi over 2. We wouldn't set it to 0. And we wouldn't aim the gun way back here. We would just turn the whole thing around. So that means we don't care about anything in quadrant 2, 3, nor 4. Our answer is going to be somewhere, excluding pi over 2, excluding 0, somewhere inside here is where our solution is going to be for the critical number, cosine 2 theta equals 0. That's kind of tricky in a way. Anyone happen to see what it might be? Well, one thing we do know is cosine itself at pi over 2 is definitely 0. Sine at pi over 2 is 1 when we're up here. So the 2 theta might be a kind of a hint on this one. Let's take this one particular angle. This one's at pi over 4. And honestly, if I didn't know what I was doing and I was aiming a gun, 45 degrees seems about right. It's between horizontal and vertical. Maybe it really is optimally right at 45 degrees. I have no idea. We're going to find out ourselves. Take this pi over 4, plug it inside cosine 2 theta, and cosine at 2 times pi over 4 turns into cosine at pi over 2 upon simplifying, and it becomes 0 altogether. Oh, sorry, I missed your question.
No, would it also work if you took the inverse cosine of this side? You get 1 time.
Yeah, I think I like that idea as well. That would work out. If you hit cosine inverse on the left-hand side, thanks for mentioning that, you would get cosine inverse of cosine of 2 theta equals cosine inverse of 0. And now that you've invoked the inverse function, that's gone. You just free up 2 theta. This would be the trickiness, but if you're fluent with inverse functions with trig, we're in great shape. Cosine inverse at 0, look to where cosine is 0, right here on the x-axis. Go up, and pi over 2 is the inverse for cosine inverse at 0. So pi over 2 would go here, divide both sides by 2, and you get theta equals pi over 4. Let me just sort of pretend like we already had that space. So either way we look at it, we've got a critical number. Thanks for mentioning that. I think that's the slicker approach for sure on this problem. Just hit the inverse function. This approach was just look at the problem and guess and pray, kind of a problem, private solution. So right here, this is the critical number. of dr d theta. Or it's probably better to say it's the critical number of the original function. Sorry, I said that in kind of a weird way. Now that we've got that, here's where the second derivative test is sometimes nice because the derivative is pretty fast to calculate in these right problems that we selected for, but it's still a pretty hard problem. Let me show you one part of the notes where, even for me personally, it's sometimes I miss this part. Let's go to our optimization section 4.7. There's the second derivative test for local minimums and local maximums that goes a certain way. Like you're mentioning, if the second derivative is positive, we have a local minimum, but we're changing this test a little bit. We're using it in this format. We just found the critical number c. F prime of c is 0. That was our pi over 4. And we're looking for a maximum of range, so we're on part A here. What we need to show is that the second derivative is purely positive for all x in the domain of that function. Keep in mind, we have a particular domain, so we can restrict our domain to the values that make sense in the problem, but we still have to show its second derivative is always positive, not just at the critical number. So let's go back to here. We indicated a domain that makes sense in the problem from a measurement in radians 0 up to pi over 2. So we have to show that this quantity is positive on that entire range. Let's write that out. We need to show d2r d theta 2 is greater than 0, or hang on, let me double check. We're looking for a maximum, so we want this to be less than 0 for all theta in 0 to pi over 2, where the 0 and pi over 2 came again from that portion where we restricted the domain for the original function. So taking another look at this, sine 2 theta from 0 to pi over 2, well, that negative is pretty nice. If we plot sine 2 theta from 0 to pi over 2, it's almost cheating using Desmos, but let's do it just for a little bit of a help. Y equals sine 2 theta, and we're going to take 0 less theta less pi over 2. So there it is. That's great evidence that we're on the right track, folks. Sine 2 theta itself is always positive on the range from 0 to pi over 2. And this sign right here says we're converting to negative. But this was kind of a weird way to do a review problem, right? We don't have Desmos allowed on an actual exam, so we would have to have said something else if this was a real exam question. Looking at sine 2 theta, you might have said, for sine 2 theta, at this range, your sine value is going to be 0 here, but we're excluding that. At pi over 4, you would have a sine at 2 pi over 4. It comes out as a 1. And then right up here at pi over 2, if you put pi over 2 inside here, this is sine at pi, which goes back to 0. So that's what we're seeing on the graph. It's positive at 1 and back to 0 right at pi. So we can argue that for all theta in 0 to pi over 2, sine 2 theta is always positive in that range. Really, we're just making an assertion, looking at the graph and see if it checks out based off this here. Now we can say, by the second derivative test, R of the critical number that we found, pi over 4, is the maximum range. But let's double check the instructions and see just what in the world we really wanted out of this. Let's see here. It says, find the angle of elevation that will give the gun a maximum range. So we didn't actually need to find that. We just need to say pi over 4 is what does it. So set theta equals pi over 4 for the maximum. So we'll just end our problem that way. We don't necessarily need to say what the maximum range would be in the function unless they asked for it. And if they did ask for it, take pi over 4, plug it inside here, and just calculate that out. That's not too bad. That would be sine of pi over 2 again. The maximum range is this. Initial velocity squared divided by acceleration due to gravity is where this is going to end up. Kind of an interesting problem. It's fun because you can imagine doing this. And once we discover pi over 2 is the critical number, it just suddenly makes sense in a certain way. I don't know if this is exactly what the military does because there's other weird things like the rotation of the Earth could mess all this up and other small effects. Well, any questions at all, folks, on getting through that optimization? Okay, and I just wanted to ask, this one was more about optimization than it was about this is a second derivative test. Did you want to try another problem that was more along these lines? Sorry, say again? Yeah, absolutely. Are you thinking optimization with first derivative? Okay, let's try that one out next. So, sorry, what was that question? Oh, that's a good question. We can use a second derivative test for something like, say, this, if it's concavity. And the first derivative test is used right here. We found decreasing, increasing. This is our author's so-called increasing, decreasing test. And then when we found the local minimum, that was the first derivative test right there. Other questions so far? Okay, let's see if we could get a good optimization using just first derivative. I think on these notes, give me a moment, the document is kind of lagging a little bit. On these notes, I'm not sure if I have another optimization, but let me double check. This one is excluded. This one was the Newton's method. This one's a different one of finding antiderivatives. I don't have any here, but I can absolutely find some. So let's go to one of these exams. I'll grab the bottom one since I think the more valuable ones are the ones on the top. And I definitely want to save it for your own personal study. That way, those problems are new and fresh for you. So let's take a look at 2014. There's got to be optimization in here somewhere. Let's see what we put the class through about 10 years ago. This one is exponential growth and decay. Around this year is when an Ebola virus outbreak occurred. So I thought, why not make that an exam question? That's kind of fun. And let's see here. Newton's method again. They really did Newton's method on that exam, but we won't on ours. They were not, actually. The way they did Newton's method was, all they did was show the structure, report the value of x2. So this is one you can do by hand kind of nicely. It's also rigged to just work out nicely as well. Let me see here. Cylindrical shells. I don't think I had one in 2014. That's kind of odd. Dropped the ball in that exam. Let's see if we have one here. 2015. That one looks like optimization for sure. So let's give this one a try. And we'll hit it with the first derivative test. Let's imagine it's something like caffeine. Who knows what this is? So a drug is administered to a patient, produces a concentration in the blood given by this here, C for concentration, ATE to the power of negative T divided by 3. This is actually a real model used for, I think they call this pharmacokinetics, studying drug concentrations. And this is sometimes referred to as a surge function. It's called a surge function because with a lot of pharmacy type drugs, especially if you're, say, injecting it or something like that, your concentration grows a little bit and then suddenly spikes and then it levels off. So they call these surge functions. Let's see. So this is the concentration, T hours after A units of the drug has been injected. A is a constant. We're not going to change the amount of drug mid-problem. So we have a constant here. It says next, determine the maximum concentration using calculus. That's kind of a weird wording. I think I stopped using that wording. We're just going to optimize, and let's go for our first derivative on this one. This is going to turn into a product rule when we calculate that first derivative. So we'll call this C prime of t, just to give Newton's prime notation a little bit more attention. First thing that happens is A is just copied in. It being constant, it's unaffected. I'll put a parenthesis here next because now we have to deal with a product rule between t, e to the power of negative t over 3. So this is constant rule, product rule, chain rule rolled into one. Let's work this out really carefully. So where the color coding is, aside from the yellow, we're going to go like this with a product rule. Let's drop in the functions, t and t in the first positions, e to the power of negative t thirds in the second position. And already right here, this is like a problem within the problem. That's chain rule. The outer function is the base e exponential. The inner function is this linear function. And let's just work out this derivative off to the side so we're not carrying kind of a large structure, multiple steps. If we take e to the power of negative t over 3, let's match that color coding first. And let's maybe even reformat the function and write it as negative 1/3 times t, just to visualize it a little bit better. Then here's how this derivative is going to go. Derivative of the base e exponential goes like this, just copies in. Inner function now is negative 1/3 t here and here. And writing it out as negative 1/3 t just makes this derivative a lot easier to visualize. T is to power 1, so it vanishes. Negative 1/3 will copy in. So this one's turning into equals negative 1/3 e to the power, and I'll go back to the original way it's written, negative t over 3. I don't know why I keep going to black on this thing. Let me e to the negative t over 3. So we've got one derivative down. We'll substitute in that stuff in that position, and then just work through the rest of the derivative. Any questions, folks, to that stage? Okay, so this 2015 exam, I think we're getting through the worst part. The derivative here was pretty rough. Even though there's not a lot of constants, chain rule and product rule and constant multiple rule all in one, just to start your problem makes it a tough one to get through for sure. But here's how it's going to settle down. C prime of t is now equal to a times. Here, we're just going to get a 1. It's multiplied by e to the power negative t thirds plus, over here, t just copies down. And the derivative of this one turned into that, negative 1/3 e to the power of negative t thirds. Okay, so we got through the derivative, and we know after we calculate the derivative, if you're optimizing, if there's more going on, spend lots of time simplifying this as much as feasibly possible. So now we're on the simplification phase of all this. Let's write this as a e to the power of negative t over 3. Here we can rewrite this just to make it easier to look at as negative 1/3 t e to the power of negative t over 3. Now, we're going to set this to 0 and solve. That means we should try to factor it a whole lot. And e power negative t over 3 will factor out of this thing. We'll have a times e to the power of negative t thirds. Inside the group, you're just dividing by that same constant we factored out. So it'll turn into 1 minus 1/3 t. So we're there, folks. This is the derivative in its most simplified form. Next thing to do, whether it's the first or second derivative test, set it to 0 and solve. We need critical numbers for the surge function up above. And a is a constant. It's the amount of drug that was injected, so we're assuming it's positive. There's no way this is 0. e to the negative t thirds has a graph that goes like this. That one is also positive. For every single value of t, this never takes on even 0. So e to the power of negative t thirds is also positive. So the only way to get a 0 is inside here. This is the only way. So we'll set this 1 minus, let me try again, 1 minus 1 over 3t has to be set to 0. So let's add a third t to both sides. Triple both sides. And this is finally the critical number of C, the concentration function. So this one is definitely kind of an adventure, but the more you practice with these kinds of things, if you can walk through this derivative really carefully and get down to this stage, it's not as bad. It just looks terrible to start. Any questions, folks, to this stage, the critical number? Yeah.
On the e to the negative two thirds, is that because technically it's just equivalent to e to the power negative 1, and that's just the inverse?
Yeah, exactly. The graph, if it was positive t thirds, would have looked like that instead, exactly. And if there was a negative sign in front, it would have looked like this instead, and we would have said there's no way it could have been positive, as opposed to not being negative on this one. Does that answer your question on that function there? Awesome. Other questions so far? Yeah. Yeah, that's a great way to think of it. Yeah, you could go right here and just literally divide out AE negative t over 3, AE to the negative t over 3. Ordinarily, that's a dangerous step, but there's no way this could be 0. And so you can just eliminate it entirely from your equation. There's a possibility. If there was any way e to the negative t thirds could come out as a 0, and we divide it out in this step, then we've lost information about that extra 0. So as long as you know it can't be 0, you're not missing anything by taking this step. You've got the real and only critical number. Other questions so far? Okay, so the actual calculus and algebra solving through this one turned out to be harder than the other problem. And the other problem had more constants. That's kind of curious in a way. Next thing we do in the first derivative test, whether you have something with context or if it's just saying find the local mins and maxes of a function, is we do this. But notice I'm writing down my number line in a really kind of weird way. One thing I did miss when I looked at the function originally was we should have probably started by saying this is a concentration function at time t. There's a good assumption that t should be bigger than or equal to 0. And so the domain of our function should start at 0, goes off to infinity. Well, I'll just write here t just to remind us the variable is t for a t-axis. So we have a very specific domain in this kind of problem. The critical number we found is 3 exactly. So the next thing we need to discover is what is the sign of the derivative here and here. So now we need some good test values. Let's pick, say, anything that looks convenient. 1 is a good choice here. You know what? So is 0. You could pick 0 on this one. It's not a critical number. It is in the domain of the function. Let's do just that. Good strategy on exams is to try to find a way to do the least amount of work possible, because you're exposing yourself to the least amount of possible errors, the less steps you have to take. So let's do C prime at 0 instead. Let's double check. Yeah, there's no issues with domain at all in this function. You can plug 0 into this first derivative, but let's see. Let's do it, say, on this line here. Just going to clear this off just for the sake of visualization. And this right here, temporarily highlighted in yellow, is our C prime of t, following those equalities down. So 0 into this location, that gives us e to the power of 0, which is a 1. So just a times 1. 0 here will also give us a 1, so times 1. And a is an amount of drugs being injected. It needs to be a positive quantity for any of this to make sense. So we got that the derivative is positive here. meaning concentration is increasing from 0 to 3 minutes. And it's increasing by a lot. It's surging into your system at this point. And what we think is it should be decreasing here as well. Let's double check why. The critical number 3 came from a group that had a power 1 on it. That means the multiplicity is odd for that critical number. And the sign, which was positive, should flip to negative. But let's double check that just to be sure. Let's throw in a 4 on this thing. C prime at 4 is going to be back to this. A e to the power of negative 4/3. Definitely ignore that negative. The exponential is still always positive. You can't possibly put a real number in there to get a negative result. So we're going to go over here next and go 1 minus, plug in a 4 for t, and we get 4/3. But 1 minus 4/3 is negative. And so that means the whole thing converts to negative right here. It's a positive times a negative number, in other words. So double checking, we put positive, we put negative. So it goes from increasing to decreasing in the drug concentration. And we want to know what is the maximum the concentration would be in the bloodstream for whatever this drug happens to be. So we now need, for our final step, because it said determine the maximum concentration, let's write out the max concentration is, take the original concentration function, so the one up here at the top, and plug in the critical number, which was 3 minutes. So this will be A times 3 here, and then e to the power of negative 3/3. Let's write that out in a slightly more simplified, less confusing form. This is just an A times 3, so we can call it a 3A. This turns into e powered negative 1. And you could leave it just like that, or call it 3A divided by E. Either way is just fine. And this is going to be milligrams per milliliter of blood. So 3 minutes later, this is how much of whatever that was injected into the bloodstream. So that's optimization with first derivative test. Any questions on getting through this one, folks? Okay, so those are definitely kind of the type of exam problems that would be okay for a real final exam. I think some of these that I did put in, you might have noticed if you look at these really close, I think these exams were a little bit harder, 2014 to 2015. That's when I was first teaching this course. Then I brought it more in line with what everyone else's final exams look like in the department. So I think these ones aren't as bad. They're more routine. And when I go to write the 2023 fall exam, it'll be more similar to the top 3 up here, I would say. Any questions, folks, so far? Okay, well, we've got 5 more minutes. How about one more problem, and then we'll call it a night. Is that all right with folks? Okay, there's still one thing that we took a look at that we didn't quite calculate. I think it's a good one to calculate because it is confusing. It was, I scrolled way too far. Let me go back down. This one right here, part F, on evaluate each derivative. This one's exceptional because this one is using the fundamental theorem of calculus, part 1. So this is how that particular theorem goes. If you're differentiating g, it'll be g prime of x. Now, although this step is optional, it's a good way to visualize what the fundamental theorem part 1 is even trying to say. It's saying if you take the derivative with respect to x of a definite integral that has x as a limit of integration, we're in fact going to up to x squared, then the derivative operator and the integral operator will now annihilate each other. We'll pick up an integrand, except this is also a chain rule, so we have to be a little bit careful. So it's t squared e to the t dt. We don't have to integrate this function. We're just going to differentiate it right away. But here's the extra confusion. This is the inner function. We're using a chain rule. And this whole thing, the integral function, is the outer one. It's hard to actually point at it because it comes with so many symbols spread out everywhere. So let's work this out really carefully. This is how we always wrote out every time if we were doing a chain rule. First thing is differentiate your outer function. And this is what the fundamental theorem says. The derivative of this integral function goes like this. And this last part is just a chain rule with the derivative tacked on. The thing that goes inside is if it was just x, we would have put it here and here, and the problem is over. But because it's not just x, it's a function of x, we'll put it here, here, and over here, we'll differentiate it through the chain rule. So next step, this is x power 4 e to the x squared times one last derivative. This is a 2x. And so altogether, simplifying this, we get 2x to the power 5 e to the x squared. Finally, this finishes off this function, but it's kind of a confusing one to look at fundamental theorem part 1 with a chain rule rolled into itself. That was the challenge problem in the homework set. I think a real exam question might have looked more similar to this. From 0 to x itself, t squared e to the t dt. If you differentiate this function, now I'm using Newton's prime notation rather than Leibniz's notation here. All that happens is you write down the integrand, swap the variable t to x. X squared e to the x. I think that's the more standard question. This one was a more challenging homework question that we saw in that homework set. Well, either way we do it, this is what the fundamental theorem of calculus looks like. But it's a confusing one on the exam because we have to recognize it. It's not necessarily in context. It could be with a problem where you're just doing derivatives because it really is a derivative kind of a problem. Well, any questions at all, folks, on running through part F on this one? Okay, well, this looks like a good stopping point for us. Like I mentioned before, the full solutions are posted on this document, so you can scroll down to the bottom, but there are solutions that look about like, oh, here it's lagging. The solutions look more like this. It's just the actual answer, not the solution. So if there's any problem out there that you would like to take a closer look at, don't hesitate to email me. I'll be very available over this weekend for emails. And just another reminder, if you're on the campus early, I will be available for office hours Monday at these times here in the office tab 268. Well, that's all I have for folks today. Have a great night, folks. Have a restful weekend. Definitely try to get lots of sleep, all that kind of stuff. And one good point of advice for final exams is definitely try to make it as similar to the way you would study for exam. In other words, if you drink a lot of coffee when you study for exam, come to class caffeinated and you'll be in great shape. You want the same mental space. But if you never drink coffee or energy drinks, coming to an exam with coffee and energy drinks in your system, you're in a different mental state than you studied. That is a recipe for something interesting for sure. It probably wouldn't work out too great. Well, have a great night, folks, and I'll see you on Monday.